In this video, we'll be analyzing the retrofit of compressed air system. I'll move to energy, I'll select from the energy drop-down compressed air, and we see the input screen. At this point, there is a number of inputs and we'll need to work through these methodically. We begin by specifying the type of compressor we have. Rotary screw is a Freddie common compressor, and then the capacity of that compressor in the appropriate units. I'm going to use 200 CFM as the capacity of my compressed air system. The motor is defaulted to standard efficiency, which we'll go with. That likely is the case. And I'll specify in horsepower that this compressor is driven by a 40 horsepower motor. RATScreen knows from its database that that motor will have an efficiency of 90.6%. I'll need to specify the air intake location, which is inside the plant, slightly warmer air, and then the system operating pressure, which we are presently operating at 110 pounds pressure. The capacity control in this particular compressor is not very good. That is, it is an inlet throttle, which actually wastes a lot of energy at part load. And one of the opportunities we'll have here is to move to a variable speed compressor. Now, we need to understand what the useful air demand is. Even though we have 200 CFM available, we're only actually using usefully in this system 100 CFM, and we're leaking another 50 CFM. So we're using 3/4 of the compressor's capacity, but 50% of that is in, or roughly 30% of that is in leaks. Next, we need to specify the hours of useful air demand. That is, for that 100 CFM, how many hours do we actually need that for? In this case, it's 12 hours, but the compressor is in fact operating for 24 hours a day. So some good opportunities for improvement in this situation. We only have one compressor, so we've completely specified our base case. We'll copy base to proposed, and now we begin to populate the proposed case situation. We are going to change to a variable speed compressor here, so I'm going to ensure that I use a premium efficiency motor, because that variable speed compressor will likely have a premium efficiency motor attached to it. We're going to change to outdoor air. Outdoor air in much of the year when it's colder outside is more dense, easier to compress, and therefore uses less energy. In this case, we will go ahead and adjust the air pressure of the system as well. We're probably operating above where we need to be. We're going to move to 100 pounds after analyzing our end uses. We'll also specify that we have a variable speed compressor, state of the art, and will deliver nice savings in a number of situations. We'll leave our useful air demand at 100. We're still using the air for what we need it for, but we are going to be aggressive on the leaks and reduce the leakage rate to 25 CFM. Next, we have to think about the hours the compressor are operating for. The hours of useful air demand will not change in the proposed case, but because we're going to shut down the compressor and we don't need it, we'll give it an hour either end of the operating schedule. So we're going to go with 14 hours as the, in fact, new operating hours of this compressor. All of these things will contribute significantly, as you can see, to the reduced energy, almost a 60% reduction in energy consumption already. Now, the total of all these measures, which would be the reduction in system pressure, the reduction in leaks, the change from indoor to outdoor air, and then the change to a variable speed compressor, will come at a price tag of $55,000. We'll go ahead and enter that, and we're now ready to look at the financial return of our project. So pretty significant savings, 67%. And when we look at our payback, we're looking at about a 2.3 year simple payback, which makes sense for this type of retrofit.